Here in chapter 12.5, we're going to be looking at lines and planes in space. And so here in multivariable calculus, oftentimes we're going to have to deal with lines and planes. And so this chapter will cover how do we express them, how do we write equations for them, and how we can do different formulas and processes using lines and planes. So to get started, we'll start with lines. And so we're going to be talking about these lines in space. And so to write the equation of any line, you always need two things. And you might remember this from like even Algebra 1. Sometimes the equation of a line is called the point-slope form. And so you kind of need those two things as well. So one of the things you always need is, first you need a point on the line. And then the second thing is, instead of slope, that we use in like algebra, we're going to use more of the generalized version of slope that could be in any dimensions, and we'll just call that a direction vector, because that's really what the slope is doing. It's telling you the steepness or what direction the line's going in, so we'll call that a direction vector. Right, and so that's true for any line. So if you take this line right here, if you have a point on it, and you have a vector that gives you the direction it's going in, then that's all the information you need to express any line: a direction it's going in and a point to anchor it in space. So the equation for a line in general looks like this. So the vector version of the equation is r of t, and I'll explain what this t is equal to r naught, right? So r naught would be the original point plus t times v. And so we'll dissect what these different components mean. So this r of t here is just your line. So this is the line equation expressed as a vector. T is what we call a parameter. And t is just it could be any variable, but it allows you to move on the line. And it is a variable that changes and gives you every point on the line. This r naught, that is a point on the line. Here's your parameter again. Right, that's where it shows up in the equation. And then this v is your direction vector. And so that's the way to write the equation of a line. And so if, for example, we picked a point to be, maybe this point is 1, 1, 1, and we had a direction that was maybe, for example, this is just an example, and the direction the line goes in from that point is maybe 2, 3, then you're starting at that point and you're going kind of in this direction. And so the last piece of information you need to get a full line, because right, the definition of a line is a straight line that extends infinitely in both directions. So the last thing you need to complete this is you need to bound the parameter so that it gives you all of the line. So in this case, we just want to say that t, our parameter, needs to go between negative infinity and infinity. And what that does is that extends this line infinitely in each direction. And so that's what the parameter is doing. Now, an equivalent version is if we just set each one of the components on the right and left-hand side of this equation equal to each other, like the x value, the y value, and the z value, you can write it in the parametric form, which would look like this. X is equal to the original x point plus your parameter times the x component of your direction vector, so the first value in the v vector. And then y is going to be the original y coordinate plus your parameter again times the second component of your direction vector, and then z is equal to the original z point plus your parameter times the third component of your direction vector. And we can kind of group those together. And then similarly, we need that where t is going from negative infinity to infinity. And that gives you the entire line, not just a line segment. So those are the two equivalent ways to write the equation of a line. Now, if we just want a line segment, that's easy to do. What you have to do is you have to just bound the parameter. So you only let the parameter extend along certain portions of the line. So, for example, let me just write that out real quick. So to get a line segment, you need to restrict the parameter t to just the section you want. So we can take a look at that in just like a little example here. Seems like I'm frozen again. Let me just give it a second to... Okay. So for example, if we just wanted the line segment, just want the line segment between, let's just give 2 points. S, right here. Between the point S, which will be 0, 3, 2, and Q, which I'll do 5, 2, 3. I'm just making these points up. So those gave you 2 points, and you just want the segment of line between them. Then let's just write the equation of that line and then bound the t value so that it only goes between those 2 points. So in that case, first we need a point on the line. So point on line. And I'm just going to use one of those points as the point on the line. So I'll just use S. So I'll let 0, 3, 2 be the point I use. And now we need a direction vector. And to get that, you can just subtract S from Q, and that gives you the vector between them. So in that case, we'll do Q minus S, which will be 5 minus 0 is 5, 2 minus 3 is -1, and 3 minus 2 is also -1. So there's a direction vector. So now let's just write the equation of the line. I'll use the vector form. So we'll get our original point. I'm using 0, 3, 2, plus t times 5, -1, -1. And so just like this would be the entire line extending in both directions infinitely long. And if you plug in different values of t, for example, at t equals 0, if you plugged in 0 for t, this whole term would be 0, and you would just get the original point. And then if you let t equal like 2, then you would get this point plus 2 times the direction vector. So that would be a point on the line 2 times the length of the direction vector away. And so you can plug in any value of t, and it just gives you all the points on the line. But because we just want the points between S and Q, we need to bound t. Right, so we're going to bound the parameter, so it only goes between 0, 3, 2 and 5, 2, 3. And we know that the lower bound at S is just when t equals 0, right? If we plug in 0 for t, then you just get that point. And now, what do we need to plug in for t to get this terminal point, 5, 2, 3? Now it actually looks like if we plug in a 1 for t, then you'll get that point. Because you can imagine if you plug in 1 for t, you can get r of 1 is going to be 0, 3, 2 plus 1 times 5 is 5. 1 times -1 is -1, -1. And then if you add those together, you'll get 5, 2, 1. Excuse me. You'll get 5, 2. Do we make a mistake here somewhere? Oh, that's right. My direction vector is wrong. 3 minus 2 is +1. That's why. So then we get +1 here, and then you'll get 5, 2, and 3. So that's 5, 2, 3. So there you go. So here, this was just a little example, but here is the line segment between those 2 points. Another thing we might be interested in is the distance from a point to a line. And that equation looks like this. So the distance from a point to a line is equal to the magnitude PS cross V divided by the magnitude of V. And I'll explain what these variables are. So S is just a point you want to find the distance from. Right, so it's from the point S to a line. P is any point on the line. It could be infinitely far away, and this formula still works. So it can be any point. And then, of course, V is the direction vector. So we can apply that in this example. I can draw just a little picture of what's going on here. So if we have a line like this, here's our line L. You might have a point S here. You're wanting to find this distance. So here's the distance that you get from the formula. And then the point P can be any point on L. So you could use a point here. It could be way out here. Any point on the line works for P. So let's try this in example 1. So you're trying to find the distance from the point S115 to this line. And this line looks like it was written in parametric form. Right, and we know from the parametric form of a line that the components of your direction vector are the coefficients of the parameter t. So we know that we can reconstruct a point on the line is, so we know a point on the line this 1, 3, 0 in this case. And then we know our direction vector is equal to 1, -1, 2. And I got that from the coefficients of the parameter. It gave me the direction vector. And I just got these straight from the parametric equation of a line. So what are the things we need? So we need this vector PS. And that's from any point on the line to the point you're trying to find. So to get PS, that vector, we'll just take the point 115 and subtract from it any point on the line. I'm just going to use this point that was used in the equation. But I could have plugged in any value of t. I could have plugged in 5 for t, and that would have given me another xyz point on the line. But I'm just going to use t equals 0 to get the point 130. So to find PS, I'll just do 115 minus 130, which gives me the vector 1 minus 1 is 0. 1 minus 3 is negative 2. And then 0 minus 5, is negative 5. Okay. So then we need V, which is 1, negative 1, 2. Something's not right here. I'm trying to find, because I have the answer in front of me, and it says this is 5 should be positive. I'm trying to find why that's the case. Point on the line. Oh, because I did this backwards. 5 minus 0 is 5. Positive 5. I keep messing up the signs on some of my numbers. Okay, and so we know V is 1, negative 1, 2. Now we just need the cross product of these two. So we need PS crossed with V. So we'll do PS crossed with V. That's going to be the determinant of our 3 by 3 matrix, the IJ, K, where we have 0, negative 2, 5. And then V is 1, negative 1, 2. Okay, so what does that come out to be? So for the I component, we get negative 2 times 2 is negative 4 minus negative 5. So plus 5 comes out to be 1 minus J times 0 times 2 is 0 minus 5 is negative 5. And then we get plus K times 0 times negative 1 is 0 minus positive 2, or negative 2 times 1 is negative, minus negative 2, so that's plus 2. So for that we get I plus 5J plus 2K. And now let's just take the magnitude of that. So the magnitude is going to be equal to the square root of the sum of the squares. So that's 1 squared plus 5 squared plus 2 squared will end up being the square root of 30. And then the last thing we need for the denominator is the magnitude of the direction vector, which in this case is going to be, so the magnitude of V is the square root of 1 squared plus negative 1 squared plus 2 squared, which is 4, 5, 6, square root of 6. And now we just know that the distance from the point to the line is this divided by that. So we know distance is equal to the square root of 30 over the square root of 6, which I believe simplifies to square root of 6 over square root of 6. 6 over, I believe that simplifies down to the square root of 5. So that's the distance from this point to this line. Okay, now let's take a look at planes in space. So to write the equation of any plane, you also need two things, just like with a line. With a line, you needed a point and a direction vector. With a plane, you need a point on the plane, and you need what's called a normal vector to the plane. So you need a normal vector to the plane. And so what the normal vector does is it defines the orientation of any plane. So if you have a plane that looks like this, then the normal vector is a vector that sticks out from it completely orthogonal to the surface. So here is the normal vector, and we usually write it with an n, a lowercase n. And you can see that if the plane changes orientations, the normal vector must change as well. So the normal vector will always define the orientation of a plane, and then the point anchors it somewhere in space. So the point on the plane says that the plane must pass through this point P on the plane. And so that will define a unique plane with the combination of a point and a normal vector. And so the way you combine those two into an equation is let a point on the plane be, let's just say, let a point on plane be P, where its coordinates are x naught, y naught, and z naught, and let n be a normal vector. So this is the normal vector to the plane, and we'll just let it be capital A, capital B, capital C. So those are the components of the normal vector. The way you combine those into a plane equation is as follows. So you get the first component of the normal vector times x minus x naught plus the second part of the normal vector times y minus y naught plus third component times z minus z naught. So these original points, so the point on the plane, are these terms here. X, y, and z, just the regular ones, those are variables. So these are variables and they let you span the entire plane. So x, y, and z, these are variables. These, x naught, y naught, z naught, those are just numbers. Right? Those are the numbers that correspond to the original point. And then a, b, and c are components of the normal vector. Now, another way you can write the plane equation, oh, excuse me, I didn't finish the plane equation. All of it is set equal to 0. So you set that equal to 0 every time. Now, another way you can write it is because, right, A, B, and C, those are scalars, the scalar components of the normal vector. This x naught, y naught, and z naught, those are also just numbers. Those are part of the point. If you distribute out the components of the normal vector to each of these terms, then you can collect all the numbers on the right-hand side of the equation and just leave the variables on the left-hand side. So it's sometimes written like this. Right, AX, which is this distributed, and then the minus the A times negative x naught is moved, that whole quantity is moved to the right-hand side. And we'll do that with each of the terms. So it's AX plus BY plus CZ is equal to D. where this d term, this is equal to all of these scalars just move to the right-hand side, leaving the variables on the left. Now you can notice that you can always find the normal vector from the equation because it is the coefficients of x, y, and z. Right, so if you were just given a plane equation, maybe in this form, then these coefficients are the normal vector. It's a normal vector to the plane. Or if it was written in this form, then the coefficients of x, y, and z are still the normal vector to the plane. So it's really helpful to know that if you're just given a plane equation, you can always dissect what the normal vector was from those coefficients. Just like we talked about the distance from a point to a line, there's a equivalent equation from the distance for the distance from a point to a plane, and in this case, the distance is equal to the magnitude of PS dotted with the normal vector divided by the magnitude of the normal vector. And then just to write out what the variables are in this case, so P is any point on the plane. S is point you're trying to find distance from. And N is the normal vector. Right, and you should also recognize that this n divided by the magnitude of n, so n divided by magnitude of n, is a unit normal vector. So it's a normal vector with length 1. So it's just been normalized. And then the last thing that's kind of interesting to know about planes is if you want to find the angle between two planes, or let me just draw out a picture of that. So if you have two planes kind of like this, I'm trying to find a picture to reference, because it can get a little tricky drawing these. So if you have two planes like this, or so here's like plane 1, and we have plane 2. Those are going to have their own unique normal vectors. Then plane 1s might be down here. So the angle between two planes is equal to the angle between their normal vectors. So the angle between two planes is equal to the angle between these two vectors, and we already know how to find the angle between two vectors. So that is that's pretty easy to do as well. It was just that the arc cosine of that term, you can just apply that to the two normal vectors, and that'll give you the angle between two planes. So let's take a look at a couple examples. So if we want to find the distance from one point to a plane, we're just going to use this equation up here. The magnitude of PS dotted with the normal vector divided by the magnitude of the normal vector. So let's take a look at that. So in this case, I'm just trying to find where my notes are. Oh, here it is. So we're trying to find, let me just do a sketch real quick of what we have. So we have a plane here, and it's going to have some normal vector. And then we have a point S, and we're trying to find this distance. That's the distance we're trying to find. So we know that this normal vector is the coefficients of the plane equation. So it's 3, 2, and 6. So we can write that out here. So the normal vector is equal to 3, 2, 6. We also need a point on the plane. So we need to find a point P. Now we just need any point that satisfies this equation. Now a really easy one that we could use is 0, 0, 1. Right? If you plug in 0, 0, 1, that definitely satisfies this equation. So for P, point on the plane, we'll use 0, 0, 1. I just try to pick the easiest points since you can pick any one. So now we know the distance is equal to the magnitude of PS dotted with the unit normal vector. So let's work on finding all of the pieces of this equation. So I'll start with finding PS. So that's going to be S, right? That's going to be S minus P, those 2 points. So S is 1, 1, 3, and the point I'm using is 0, 0, 1. So we'll get 1 minus 0 is 1, 1 minus 0 is 1, and 3 minus 1 is 2. So let me use vector brackets. So there is PS. Now I need to find the unit normal vector. So the magnitude of n, that's going to be equal to the square root of 3 squared plus 2 squared plus 6 squared, which in this case equals the square root of 49, which is actually 7. So now I can use that to find n divided by this is just going to be the components of n divided by 7. So that'll be 3 sevenths, 2 sevenths, and 6 sevenths. Okay, so now we just need to dot together PS and this unit normal vector. So PS dotted with the unit normal is equal to, right, we multiply the components and add them together. So we'll get 1 times 3 sevenths is 3 sevenths, plus 1 times 2 sevenths is 2 sevenths, plus 2 times 6 sevenths is 12 sevenths, which ends up being 12, 13, 14, 15, 16, 17, the beautiful number 17 sevenths. And now we just need the magnitude of that. So the magnitude of 17 sevenths. And since 17 sevenths is already a scalar, we just know that that is equal to 17 sevenths. So that's the distance from this point to this plane. So that's the distance we found. Okay, now example 3 is the grand finale Ghost Pepper Challenge of all point and plane problems. If you can figure out this example 3 question, then that would really prove that you have a great understanding of how points, lines, and planes interact. So I would encourage you to take a second to pause the video and try example 3 on your own, and then check in and we can work it together. So I'll give you a second to do that. And now I'm going to get set up. So we're trying to find the equation of a plane containing the points P and Q, and that is perpendicular to this other plane. So it might help to start by drawing a picture. So let's draw a picture. Oops. Just to sketch out the scenario. So you were trying to find the equation of a plane. So this is the one we're trying to find. And we know that that plane contains the points P and Q. So P and Q lie in this plane. And we know that this plane has to be perpendicular to this plane. I'll do it in this orange, red. So we know that plane P is perpendicular. So here's P. It's perpendicular to the plane we're trying to find. So where do we start? So what are the two things we need to write the equation of any plane? We need a point on it, and we need a normal vector. So we already have a point on the plane. We can use either P or Q. It doesn't matter. And we need a normal vector to the plane. So we need to find this. And so the real intuition for this question comes from how do you find this normal vector? Well, we already know one normal vector. We know the normal vector of the perpendicular plane. Right, the perpendicular plane has kind of this normal vector. That one. And we can write that out here. It is 2, 3, -4. Now, how do we get a vector that is perpendicular to this plane? Well, you'll have to recall from the last section, when we learned about the dot and the cross products, there was a unique characteristic of the cross product was that whenever you took the cross product of two vectors, it would always give you a vector that was perpendicular to the two you took the cross product of. And so using that facet of the cross product, we can use it to our advantage to find a normal vector. And so the clever form of the cross product we're going to use is we're going to cross together this vector, PQ, because we know that's in the plane, and this vector here. We can cross it with the normal vector of a perpendicular plane, because we know those will both be perpendicular to the normal vector we want to find. So that's the intuition for this problem. So to find N, we need to cross PQ. So we're constructing a vector in the plane. We're just making it out of those 2 points. And this N. That will give you a vector that is perpendicular to the plane. Oops. So let's do that. So first we'll find PQ. So PQ is just going to be 2 minus -1, which is 3. Wait, it's going to be, 2. Oh, sorry, -1 minus 2 is -3. Then we get 2, and then 1. And we know our N, right, this N is 2, 3, -4. Then we just cross those two together. So we'll do PQ crossed with N. So -3, 2, 1, 2, 3, -4. That comes out to be, I'll just save you the calculation. It comes out to be what is it, 11i plus 10j plus 13k. So this is n. This is the normal vector of the plane we're trying to find. So now, writing the plane equation is really easy. So the plane is going to be those coefficients of the normal vector, right? Let's get our plane equation, where it's the coefficients of the normal vector times the variable x minus a point on the plane, the variable y minus the y point on the plane, and the variable z minus the z point on the plane, set equal to 0. So that's going to be 11 times x minus, and for the point on the plane, I'm just going to use p. You could equally use q. They would give you the same plane. So x minus 2 plus 10 times y minus 1 plus 13 times z minus 1, all equal to 0. Or you can distribute this out to be 11x minus 22 plus 10y minus 10 plus 13z minus 13 equal to 0. And now move all of these just numbers by themselves over to the right-hand side, and you'll get 11x plus 10y plus 13z is equal to 45. So all of these are equivalent. This is that. And these are the two forms we saw up here. So sometimes the plane can be written this way, and sometimes it's written this way. Now when I write planes, I always will default to writing it in this form and not worrying about distributing out and collecting, because that's just more steps for potential error. So just leaving it in this form, set equal to 0, will always give you a correct answer, and it leaves less opportunities for mistakes to be made.